welcome to episode 28 of the Data Science Decoded podcast. I hope you're well. I'm here with Mike and Nir. How are you guys?
I'm
Doing
okay.
good.
We are good. We're good.
Yeah, it's been a few weeks.
It's been
How things are going?
3 weeks, I guess.
Yeah.
3 or 2 weeks, yes. But next we'll try to keep it weekly and not monthly as it comes out last time. Let's say
Yeah,
We'll try to do it weekly.
but we won't give up.
Yeah, we're not planning to give
Consistency is
up.
key.
Yeah. Everything is good here. Same old. Working, sleeping, working out, working, sleeping, working out, repeated.
Yeah, more or less here.
Perfect. Same. Okay, cool. So, to our listeners, today we have a paper from 1970. So it's around 50 something years, 55.
Mm-hmm. Yep.
But it's super influential. And many data scientists or people in data don't know the theory behind it. Only I, a few years ago, heard about it. And recently I saw the paper and I said, oh, we should go over it. It's quite nice. So the paper is titled Space/Time Trade-offs in Hash Coding with Allowable Errors, which sounds super cool. I don't know, space-time is... Oh, wait. Space-time is usually something we attribute to physics, right? So when you hear a title like that, you think, oh, it's physics, but no, it's actually computer science. And it's about hash coding. And the idea here, just in high level, let's say you stored a set of messages, could be as large as you want. Now a new message came in and you want to check if it's in the set, if it's stored. Yes or no.
Mm-hmm.
And it was published 1970, as I said, by Burton Howard Bloom, and he's Jewish. And he worked back then in a company with the name Computer Usage Company, which sounds like, I don't know, in some kind of film, in a utopian film. It sounds like the bad company, the Computer Usage Company. And I checked, and it was one of the first companies that did consulting in software. So in 1970, it was one of the largest companies, and that's why they published papers and they dealt with a lot of hard problem in computer science and software engineering. So what are your thoughts after reading? Mike and Nir, were you familiar with Bloom and what's called Bloom filters prior to reading it?
I'm pretty much familiar with this concept of Bloom filter, and actually I used it. Last time it was, I guess, 10 or 9 years ago. But beforehand, in my second degree, which was computer science and math, I studied it in one of the first courses on classic computer science, and I don't remember the exact name. And also then I worked for Samsung, which in the department of solid state devices. Techniques like Bloom filters and its generalizations were used to develop methods for a so-called flash translation layer, the layer which actually connects the media or solid state device with your file system or your operating system. And as we need to somehow connect physical and logical addresses, Bloom filter was very handy. It wasn't It wasn't a classical Bloom filter. It was some kind of generalization, but still, the concept held.
That's cool. What about you, Nir?
No, that's the first time I've ever heard about Bloom filters. Electrical engineering, that's my field, and we didn't learn about this stuff. But it's a very reading about it was no problem at all, and it's very immediately you try to, I guess, outline all the relevant disciplines that can use this kind of very simple, if I may say, idea. But the simplest ideas are these are the ideas that actually catch and serve humanity. So I was not very, after reading it, I was not very surprised to learn that it's everywhere. This filter.
Yeah, and I would say also I only stumbled upon it while working, mostly in databases. And again, also my degree, I didn't learn it because it was in computer science. So anyways, I'll start by reading the abstract. Then we'll go over the method that most people used until his paper. So he describes it as like the status quo. And then he gives two methods that are better. And one of them is what today we call the Bloom filter. So, okay, his abstract. He says, in this paper, trade-offs among certain computational factors in hash coding are analyzed. The paradigm problem considered is that of testing a series of messages, one by one, for membership in a given set of messages. As I said, checking if a message already exists in some kind of, let's say, on your computer. Two new hash coding methods are examined and compared with a particular conventional hash coding method. Okay, so he gives the conventional and then two improvements. The computational factors considered are the size of the hash area, the space, so how much space it takes to store the hashed messages, the time required to identify a message as a non-member of the given set, so reject time. So how fast can I say that some element or some new message is not in my set of messages, and an allowable error frequency. Maybe I'm allowing some false positives. And he says the motivation, the new methods are intended to reduce the amount of space required to contain the hash code and information from that associated with conventional methods. The reduction in space is accomplished by exploiting the possibility that a small fraction of errors of commissions may be tolerable in some applications. In particular, applications in which a large amount of data is involved and a core resident hash area is consequently not feasible using conventional methods. So he says when there's big data, in quotes, and something that takes a lot of memory to store. So at the end, let's say classical method is I just store all the messages, and if a new one comes, I just compare it one by one. You understand, as you have more data, you need to store more messages, and it becomes a problem.
By the way, Daniel, I think it is not the only problem. Sometimes you don't have any choice. You have to store these messages, but in order to understand whether the message you want to store is already stored, the only option without these hashes is just go to your slower memory and just starting to checking out with all the messages you stored. And sometimes it is important to understand whether the message which arrived is already stored in your solid state device, say. And if you don't use Bloom filters method, Bloom filter based methods, the only choice is just to go to your slow storage device and to check all the data stored there. And
it one by one. Slow. That's what I meant. Or you plan something else.
So the main consideration is time. You have to store this message. You don't have a choice. But the comparison time can be huge if you don't use smart methods like a Bloom filters.
Okay, cool. got it. I would just add that Bloom filters can also reduce size of storage, right?
How can it be? You need to store your messages. Okay.
So we'll get there. We'll get there.
Okay. Okay. Okay.
He says here, in such application, it is envisaged. How you say it, Nir?
Envisaged. I don't know.
It's like envisioned. I don't know. That overall performance could be improved by using a smaller core resident hash area in conjugation with the new methods, and when necessary, by using some secondary and perhaps time-consuming tests to catch the small fraction of errors associated with the new methods. I think that's here. He says you can reduce also space. He says analysis of the paradigm problem demonstrates that allowing a small number of test messages to be falsely identified as members of a given set will permit a much smaller hash area to be used without increasing reject time. So you can keep the time the same, allow more errors, and then keep it in a smaller space in your memory or whatever. Cool. So now we'll go over the.
So Daniel, what he says here, to my understanding, and correct me if you think it's not right, but he says let's reduce the amount of space needed, but the penalty that we will get due to this is sometimes we will get a false.
Exactly. We would ask if a message is in a set, and then it might say no, but it is.
Okay. Yeah, that's what I understood. Okay.
Now let's go over the methods. He gives an example. He gives introduction, then a sample application. He talks about the problem of hyphenation. So if you have a text and you wanna add hyphens to it, so he says, okay. He says let's assume that a few simple rules could probably hyphenate 90% of all English words. So 90% of it could be like rule-based, but a dictionary lookup would be required for the other 10% because it's too complicated. And then he says, suppose the dictionary is too big to fit in available core memory and is therefore kept on a disk. So that's how, up to his, let's say, paper, things were used. And then he says, okay, let's reduce the constraints by allowing a few words to be falsely identified as belonging to the 10%. So let's make mistakes a little bit. A hash area for the 10% might be made small enough to fit in the core. I think core is like more like cache memory today. So that's like the motivation. Let's reduce restrictions on and allow a little bit of errors, and then we can compress it more, right? So in my view, this idea of is more like compression. We're trying to compress information to a degree.
Yes,
but I'd like to emphasize that it is not lossless compression.
Exactly,
because we're talking about the hashes, which are much shorter than the original message.
True, and you allow errors, meaning you can hash different messages to the same code. Same code. So anyway, now he starts with a conventional hash coding method. I don't know if I want to read it. It could be confusing. The idea here is if we have n messages, we use hash function and just hash them to some place. And then each message is hashed to a different place. And then at test time, let's call it test time, when a new message comes in, we use the same hash function. It's also hashed, but then we still compare the output of the hash function, which is also some kind of a message. The idea is to keep it correct, never have like errors, right? So then you can say with 100% at test time, like if a message is present or not. And here it says like the algorithm here is like iterative. And then that's previous to like the status quo prior to his paper. Then he says, and again, it's 1970. So maybe all of the algorithms were more basic. And then he says there's 2 hash coding methods with allowable errors. Now he says, okay, let's allow errors. And the first method, he says, it's derived in a natural way from the conventional error-free method. The hash area is organized into cells as before, but the cells are smaller, containing a code instead of the entire message. So he says now, like, let's do the hash function. We'll get a message. We only store part of it. So by definition, now we're gonna use less space. But what's the problem? We allow errors. Because we just threw away some part of the message. And he says, since the codes are not unique, as were the original messages, errors of commission may arise. So it's like the naive solution to reducing space is just throw away some of the messages. Okay, so up till now, we're good. And now method number 2, which is what we call today a Bloom filter. And he says, method 2 completely gets away from the conventional concept of organizing the hash area into cells. And then he says the hash area is considered as n individual addressable bits. So now I have n bits that could be 0 or 1, flipped on or off. And then he says at the beginning, all bits in the hash area are set to 0. Next, each message is set to be stored. Each message in the set to be stored in hash coded into a number of distinct bit arrays. So now every message is hashed to a number that flips on the bits in this array of zeros. So now, like in a sense, the hash function, the output of a hash function is a binary sequence of zeros and ones, and all the ones go and turn on the ones in my hash array, right? So if I have n messages, each one turns some of the bits on, and if it's already on, I don't do anything.
By the way, Daniel, we have here dhash functions, and as far as I remember, these hash functions should be some kind of independent, or at least some. I'm talking about with some use of notation. Let's say it this way. So these functions should map. This hash function should map your messages, your message, in some unrelated location on this n bit array. So if all this, if all this hash function map some message into just one bit, it is kind of a problem. I don't remember how it is done. There is, I guess, there are some seeds, but the choice of these dhash functions is very important here.
Yeah, you're right. And D is the number of bits that will be turned on per message.
Yes.
Okay. And yeah, you're right. He also talks about it being independent. I don't know what does it mean exactly mathematically, or if he really knew about it. But then he says to test a new message. So now we're in test time. A sequence of D bit addresses is generated. So again, this message lights up D bits. And if now we go to our array, of length n, if all those d bits in places that are represented by those bits are 1, the new message is accepted. It means it's in the memory. If any of these bits is 0, the message is rejected, so it's not present. And then he says on the trade-off, right? So we can control this d, we control the n, what's the size it's going to take in memory, and then you have degrees of freedom. So he gives the intuition. He says intuitively it can be seen that up to a point of diminishing returns, the larger the d, the smaller will be the expected fraction of errors.
Yeah.
Okay, and then he talks here about a priori things. It's just confusing. And then he says, consequently, for any given hash field size n, there is a minimum possible accepted fraction of errors, right? So the larger the n, the less errors will be, because the probability of the same messages will be hashed exactly to the same number of bits that are on is lower, because I have much larger positions to be hashed in.
Daniel, by the way, I think the choice of D is some kind of trade-off, because you want D to be very large, because from the one on one hand you want to decrease your false positive, but if your D is too large and you store a lot of messages, all these bits can be switched on by unrelated messages, so you get false positive. So we have a kind of trade-off here on D.
Yeah, you're totally right. Okay, so then he goes on and talks about the computational factors. So he defines like how many errors, fraction of errors is p. There's a definition, and now he does some analysis mathematically. Not complicated, but to me it was confusing because there was a lot of definitions and semi-hand waving. So we won't go into it, but the idea here, it defines space and time, the trade-off. So space is how much storage I need to hash everything and keep it in memory. Time is how much time it takes to retrieve, to understand if a message is present or not. The longer it takes, it's worse. I want to fast to know if my current message is stored or not. And then he does an analysis between all the 3 different methods that we discussed. And of course, his method is better, which makes sense. You can see it here. So to our listeners, there's a plot of the x-axis is time to retrieve or to check if a message is present. The y-axis is space, how much space we need to store it. And his method is better on both compared to the first method, which is just like a lossy, naive hash function method.
By the way, the time issue for us in 2025 seems a bit strange, because in order to compute your hash is matter of microseconds, and you just and the comparison as well, even if your array of bits is very, very large, say 1 megabyte or maybe 100 megabytes, still the time after you compute your hashes, the time to compare with all the bits which are ones is quite negligible. But in this paper was dated 50 or 60 years ago, I guess.
55,
55, and I guess then these computations could be quite heavy. And also there is one more factor, okay? And this factor is very important. And then this factor is how many messages I can store this way in order to work with some predefined of a false positive probability. Okay, as far as my n is larger, I can save more messages in this way, And I think there are many papers about Bloom filters. I think 10 years ago, I think these formulas appear. It is much simpler way. You can just look at Wikipedia, and they have all the derivations. Okay.
Yeah, so I'll add to what Mike said. There's a lot of generalization and improvements on Bloom filters for sure. Almost nobody uses the naive Bloom filter anymore. But I just want to add that every database has implementation of Bloom filters. So, we're all using databases, even if we don't want to. Nir, you read a little bit about the usage. So
Yeah.
what else did you read?
Yep. Before I answer that, I want to also look at this table and just the table that you have there on the page. Yeah. So, for example, go to the 1/16, the fourth entry of the table, the fourth row.
I'm trying to zoom in.
So the fourth row, I will read it to the readers, to the listeners. The fourth row, saying that with allowing an error of 1/16, which is I guess like 6.625% error
rate. Yeah.
We reduce the disk space by almost 85%, which is it's not linearly connected. It's not linearly. So with just a small bit of error, you get a very large saving on disk space, and that's the genius of this space-time interaction, I think. And to answer your question now, Daniel, I think the application that most resonated with me in terms of understanding, because I'm not a computer scientist, was spam filtering. So let's say I get an email and the spam filter is trying to assess whether this is spam or not. So let's say this is an address, email address, and now I have to look it up on all of the email addresses of the spammers, which can be hundreds of millions email addresses, maybe even more, maybe billions, because they change it all the time. So to search billions of entries or billions of entries will take a lot of time. So they use Bloom filters for that. And even if they have an error, they can still go and search or do some AI on the content then. So it's using Bloom filters and then some mechanism to reduce the error even further after using the Bloom filter. So that's what resonated with me. But there is a lot of applications, I guess, also in your field, Daniel. Like you always post about Spark, which I don't really understand what it is, but I bet this database has some sort of a Bloom filter behind it. I don't know.
I think, Daniel, it's the time of a 1-minute lecture about Spark, because I think it is not exactly database.
Yeah, it's similar, but it's not exactly. It's missing some key properties of databases. But I am specifically now in the big data field, and Spark is probably the most used tool. And the idea there is to do computation. But when I say computational compute, I mean more like think about tabular data. So you have big tables, and you want to sort them, join them, and do queries that are like SQL type. So when the data is really big, many companies use Spark. And that's true. Spark has Bloom filters. And that's how I originally heard about Bloom filters. I just want to add that while reading the paper and also thinking about the idea, to me, I first, following our previous episodes, the idea of dimensionality reduction. Right? I want to reduce either time or space, but I have some message. And now hash function at the end also does some kind of coding, right?
Yeah.
So I just thought to myself, okay, so this idea of Bloom filters, although the derivatives are like heuristical dimensionality reduction, but maybe for specific use cases, it's better to come up with a better hash function, right? When instead of hash function, we can say, some kind of coding, which we can learn given a lot of data, right? So I don't know if there is something like that. Probably there is some kind of improvement to this algorithm where the hash function is learned from classical machine learning methods. And then you can improve both time and space for a specific use case, right? Because this method is like general. So what are your thoughts about what I'm saying?
I don't know. I guess my wild guess is that there are papers which are trying to do that, because most of the ideas that I have been thinking about. Eventually, I found some papers which discusses some idea which is close to my thoughts. For currently used hash functions, they are I'm not sure how were they built, like Murmur, like SHA, and SHA 256.
56, yeah.
Yes, all this stuff. I don't remember how were they built. I think they were based on some cryptographic assumptions, which I don't remember what does it mean. I just remember this term, cryptographic assumptions, and but I guess
and it sounds good enough.
Yeah, it sounds good enough, but I admit that I don't remember what is it, and if you don't remember as well, you can use some average LLM to ask it. And a couple of more remarks. We didn't talk about false negatives. And why didn't we talk about false negatives? Because Bloom filter doesn't have false negatives.
Exactly.
Okay, false negatives is inherently zero for Bloom filter. They have also only false positives.
Yes.
This is the first remark. And the second remark is some very cute generalization of Bloom filters, which is called countable Bloom filters. In some applications, I don't remember why did we use it in Samsung. I admit that I don't remember, but we use countable counter-based Bloom filter. Instead of saving one bit for each message, we save a counter. And for example, if the message come say 3 times, the counter will be 3. So instead of let's assume that the maximal value of this counter is 16. So instead of saving a single 1-bit array, we are saving 4 1-bit array, because 2 in the power of 4 is 16. And then I guess that the task is to detect messages which are coming a lot in order to cache them, to store in some fast.
I'll tell you more. The counting Bloom filter also helps if at some point you want to reduce the number of messages.
Okay.
So regular Bloom filter, it's a problem. Let's say you added all the messages, and then you have ones and zeros, and now you want to remove a specific message from your storage because it's not interesting anymore. So even if you compute the hash of that message, you cannot go and reduce and make the ones to 0, because you might remove some other message or affect it. But when you have a counting Bloom filter, now you can do it. You can, if you want to remove a specific message from your storage, you calculate the hash and then you go and reduce the counter.
Yeah.
And then you're not affecting the others, and then you removed it.
Okay,
so
but here there are still, you need to allocate how many bits, what's the maximal number of bits.
Yeah.
This counter,
it takes more space.
Yes,
it takes more storage.
Yeah. You need more space, and also what happens when this counter reaches its maximal value. Then I remember they are doing this. just zeroing the first most significant bit.
Yeah, you do it. That
all
there
these
is some.
things.
I know. I remember that. Yeah, yeah.
Yeah,
There is some kind of a trick.
I
You
think I
move
have
to
a
the next
pattern.
one.
I think
Ah,
I'm pretty sure it was submitted, but I'm sure I'm not sure that there is a real patent based on it. Maybe it was refused, but there is one pattern which
rejected.
used the bloom filter for some caching technique. I don't remember, but it was 10 or 9 years ago. But I'm pretty sure I did something like that.
The perks of being incorporate.
Yeah,
You write patents that you don't remember you even wrote, and you have no
Yes,
idea if it even
yes,
accepted.
yes. And I don't have
Uh,
so many patents, I have maybe 7 or 8, not so much, but still, it doesn't belong to you, so you don't use your storage in your head to remember. You don't waste storage in your head to remember all this stuff because it's not yours.
because you have Bloom filter, new biological
Yeah,
one
yeah, because Bloom
that,
filter in our
that
head
is optimized by evolution. Let's go.
for the really important stuff, and not for some corporate patents.
Look, when you ask me a question, let's say a yes/no question, or like if I remember something, I don't go over every memory in my mind and
Yeah.
do like yes, no, yes, no. I know it straight away. So yeah.
Yeah,
By the way,
Biological
be like a
computing.
Bloom
Let's go.
filter. Let's always say no and then check if it's really the answer.
by the way, we have not talked. We have not discussed because deep learning and Bloom filter are quite far concepts. But now you just reminded me because there is architecture. There is kind of there is a family of methods which is called adaptive architecture. Okay, you can build adaptive transformer. And what is adaptive here? There, adaptive is a number of computations for each input. Sometimes you decide that you output your final prediction after only 2 layers of transformer. If you are pretty sure about the output, you don't need all these 100 layers of the transformer. You can finish after 2 or 3 layers. And there are quite advanced architecture which implement this idea, but still they are not mature enough to be used in production. Okay, I don't. I think I haven't seen such adaptive approaches in real big scale applications. But maybe I'm wrong here. And
so you're saying they share similar concept of if something is easy, I don't wanna waste computing the whole my 7 trillion parameters. I wanna
exactly.
Yeah,
it's the second side of sparsity.
Mm-hmm.
Yeah,
cool. It makes sense.
So thank you for that. I had fun, and we are in 1970 this episode. So let's see what will be the next one. No promises.
But I don't know what are gonna be the next paper, but I know when it's gonna be. Next Sunday.
It's on a week, yeah. In a week.
Yeah, we are doing it weekly from now. We are doing our best to do it weekly and not monthly and not bi-weekly or try weekly.
Cool. So have a great evening, everyone, or a great day, and see you next time.
Bye.
Nice.
Bye.